Probably turn that on. All right, so the definition is going to be the same no matter what I'm marginalizing. All right, so if I'm talking about cost, revenue, or profit, it is whatever that is. So revenue per one unit of input, one additional unit of input, or profit per one additional unit of input. In either event, we're talking about a ratio or rate of change at a particular moment, also known as a derivative. All right, so that was the world's longest preamble for something very simple. It just basically tells us that anytime I see the word marginal, then I can just swap it out for the word derivative. All right, but probably figured that out. Said C prime of x. The prime means derivative, so it had to mean the same thing. Just the question is, of what the connection was. All right. So with that in mind, any of these questions become pretty straightforward. Not always easy to do, because when you're looking at an example that's got 8 parts to it, you're not thinking to yourself, oh, this must be an easy problem to do. But straightforward is not always the same as easy. You have a process to follow. Find the marginal cost. That's the same as saying find the derivative of the cost. Which would be what? 6. All right. Find the marginal revenue. We're capitalizing R for revenue, so R prime would be my marginal revenue, which would be, it's a little off the screen now, so let me just bring it back in. My marginal revenue would be what? All right. Then it asks us to evaluate some things. All right. And then interpret. The interpretation is going to be important because, and you could kind of sort of rely on that as a rule of thumb, where if the math is not difficult, then something has to balance out that fact. And usually there's some sort of analysis component. All right. So I would need, nope, that's not a C. R prime of 1500 and C prime, R prime of 4500. All right, I'm not going to do that right now though. I'm going to sit tight on that. Because part D is telling me to graph, determine the break-even points. Then I have to find the profit, and we got to do a bunch of things it looks like on the calculator. So why not just do this on the calculator too? So I'll come back to that. E is asking us to come up with a profit function. Well, that's nothing new. And I'll just put D over here because I'm going to create a graph. So E is going to be P of X. The relationship between revenue and cost is such that if you were to subtract the two, revenue minus cost would give you profit. Bless you. So if you know, if you know what the word revenue means, then you don't need anybody to tell you that profit would be the difference between the two things, because one is income and the other is expenses. So profit would naturally be the difference between the two. But also, it's something you saw before in previous courses, so this part is nothing new. Marginal profit would be the derivative of profit. And I already have that, really, because it's the difference between the marginal revenue and the marginal cost. So I can just do it all again based on what I produced in E, or I just take my answers to A and B and subtract those. Simplify if you want. Like I said, we're going to do this in the calculator in a minute anyway, so I'm not going to bust my hump trying to do things by hand too much. All right, so P prime of 1500, P prime of 4500, and the interpretation that goes along with those. And then the point of diminishing returns. All right. I'll cross that bridge in a few minutes. But let's kick over to the calculator now and put our two functions in, and at least kind of get a little ways down the line here. I guess I could just read it off of there, but I want to see the actual problem. All right, so we have cost, we have revenue. Now, in this process, I need to find R prime of 1500 and R prime of 4500. They don't really tell me to do anything with the cost function aside from helping me to find profit. So let me just pop in the revenue function, 20x minus 0.0033 x to the second power. All right, so I need the derivative at 1500 and 4500. I'm also going to need the graph, but let's just take care of the derivative first. All right, so I can do it a couple of ways. One would be to come up with a viewing window and use the value function. That's not unreasonable. The other way to do it would be to just evaluate y4, because y4 is the derivative of y1. So if I go into my home screen and just type y4, so alpha trace y4, and then just pop in the 1500, and then pop in the 4500, I would get the values that I need. Benefit of doing it this way is that you don't have to worry about the window. Right? If it's a quick calculation and that's the only thing you need to do, then this is a good approach. So alpha trace y4 to come up with the y4 on your home screen, and just type in what your evaluates. All right, so we get 10.1, and I'll just make a note of what the numbers are, and then we'll address them in context. All right, so what this is telling us is the additional revenue, or the revenue by including one additional input item. So however you want to phrase it, but the idea is that you're going to gain a certain amount of revenue or lose a certain amount of revenue for each additional item at a particular moment in time, in this case for a number of items produced. So really, I mean, if you want, you could just kind of rephrase this expression here in context. Additional amount received when producing one more input item. Well, the input item is table saws. So this would be 10.1 units. Well, it's cost and revenue. They didn't mention any units, so it's implied to be just regular dollars. So the revenue you're talking about a positive derivative, so that's an increase. There's increasing. At $10.10 for each additional table saw, or just saw. All right, positive derivatives are positive slopes. So it's going up. It's showing an increase. Negative derivatives, negative slopes, showing a decrease. So in the second case, it would be that the revenue is decreasing at a rate of $9.70 for each additional saw. All right. I just kind of paraphrased a little bit. Save a little space, gets the job done. Yeah, the revenue decreases at $9.70 for each new saw. All right, so definitely going down. So somewhere between 1,500 saws and 4,500 saws, we went from a good situation to a maybe not so good situation. Right, so we've hit somewhere along the lines a point of diminishing returns where we're no longer increasing our revenue by increasing the number of saws we produce. So then it begs the question, well, why produce more saws? You know, is there some sort of optimal value? Is there some sort of perfect number of saws that we could produce that would allow us to optimize our revenue and then therefore our profit, right? So that's kind of what we're working towards. All right, so that was C. Now D is saying to create the graph of R of X and C of X. So I'm just gonna go back to my Y equals menu. I'm gonna turn off my derivative. I'm gonna look at the revenue function and the cost function. Cost function is 7,200 plus 6x. Now I wanna graph that. All right, so I need a good window. Well, the questions that they're asking involve really large values of x, 1,500 and 4,500. So I'm going to want something pretty big, I think, in terms of a window. So I don't know if you want to go just north of 4,500, like 4,501, or if you want to go something, much further. Personally, I mean, I would like to have at least this number here to be kind of a central value in my screen. I mean, it really doesn't matter, but that's my mentality. It might be overkill, but I would tend to go, okay, if they want 4,500, let me just double that. I'll go 0 to 9,000. And then zoom fit Y min, clear, zoom 0. So the calculator figures out the best viewing window related to the X min and X max that I put in. So I kind of overdid it. I went too far, but at least I got the important information, right? So the curved graph is the revenue function. Revenue being negative would be a problem, I think. I mean, companies go out of business all the time. So it's not impossible that you could have something below the x-axis in revenue. That would just mean that your business has completely failed to the point where not only you're making table saws, but it's costing you money on top of producing the table saws, right? So the amount of money that you're bringing in is negligible, and to the point where you actually, instead of bringing money in, you're paying people to take the table saws. So that would be something like nobody bought your table saws, and now you have to pay to dispose of them. So there is a case for negative revenue. It's just, it doesn't seem to make sense in this situation. So it looks like, this would be, round here is like 4,500, right? So maybe if I do like 5,000. Because I don't need to see that much negative area. Zoom fit the Y min, so clear, zoom 0. That could be good. All right, so let's get a graph here. Just do a sketch. Get the important details in there. Oh.
So this would be X. This would be Y. Highlighted the wrong thing. I'm going to need those break-even points. All right, break-even points would be where cost and revenue are equal to one another. So that's just a fancy way of saying intersections. So second, trace, 5. Scroll to the first intersection and hit enter, enter, enter. So you get about, I mean, I only need the X values at this point, I think. Take a look. And the regions of gain and loss. So about 598.81 roughly. And 3643.62 roughly. All right, so if we're addressing gains and losses, we have a lot of things to really cover here. A word about the decimals, because oftentimes in the past, and nobody said it here yet, so that's good, but they would say, well, you can't have 0.81 of a table saw. And my answer with that would be, or for that would be, have you ever built a table saw? They say no. Like, how do you know? They'd be like, oh, okay. So basically, I mean, unless you have direct experience in a particular area, I mean, you can't make a claim one way or the other. Who's to say somebody didn't get fired like mid-table saw production? Or yeah, maybe they're like, you're doing it wrong. Okay, yeah? Well, I'm out of here. I quit. Take the apron off. Safety goggles, throw them down. And then they leave it 81% completed. Specifically 81% completed. Yeah, I mean, there's a case to be made. Anyway, so regions of gain and loss. Well, gain would be where revenue is greater than profit. So you just got to keep track of which function is which. In this case, it's easy because one of them is quadratic and the other is linear. It's when you have two funky functions, that's when things can kind of get a little crazy. That's when knowing which one's your y1 and which one's your y2 becomes really helpful. But in this case, I don't think you need that. So I just need to know the area where the parabola is above, physically above, on top, vertically above of the line. All right, and so that would happen in the interval between 598.81 and 3643.62. All right, so anything in that interval, we'd be operating at a gain. All right, so, but we know that based on what we made in terms of calculations, the marginal revenue at 1,500 and 4,500, that even though we're still operating in the area of gain with both of those numbers, well, actually no, just the 1,500. Okay, good. I didn't confuse myself too much. So 1,500 falls in this interval, so that explains why we have a positive derivative. The 4,500 does not, so that could speak to why that has a negative derivative. All right. And also, I mean, lousy diagram notwithstanding, you can see that, you know, in any parabola anyway, there is a part where it'll be increasing, then it zeroes out, and then a part where it starts decreasing. So anything after the turning point, the derivative is going to be negative because it's going downhill. All right. So we do have a nice value here where the derivative goes to 0, And at some point, we're going to want to take note of what that is. Now, in terms of the loss, operating at a loss would be everything else. So where cost is less than revenue. Oh, I just wrote the same thing, just in a different way. That was so stupid. That's a Monday morning mistake on a Friday. All right, so revenue is less than cost. All right, so you're taking in less than you're shelling out. That would be everywhere else. So that's on the interval of 0 to 598.81. And then 3643.62 to N. We wouldn't say infinity because infinite table saws, that just sounds horrific. I wouldn't want to live in that universe. When we say N, we're saying we're going to some finite large value, right? That's the definition of N in general. You can go brackets or parentheses on the N if you want. It doesn't make a difference, right? Because we're defining it as something finite. You can go either way with that. Okay, so then we address profit. Profit, again, is revenue minus cost. So we had the profit function here, but I need the marginal profit. Now, normally I would say just take y1 and subtract from it y2, but no. I got to take the derivative of it anyway, so it's really not as user-friendly to do it that way. One thing you could do, and this takes a little foresight, you could put your revenue function 20x minus 0.0033x squared into y2, and then 7200 plus 6x into y3, just so you have your revenue and your cost functions as separate functions, so you can graph it and do things with those. And then in y1, do y2 minus y3. And then just turn off y2 and y3. All right. So that would be your profit function, y2 minus y3. But even still, I don't need to see that anyway. I need marginal profit. And that's assuming you were unwilling to do any of this work, or you were perfectly willing to do it. It's just you had some nasty function that you didn't know how to find the derivative of, or time was just not on your side. It's like, I need time for other questions, so let me just crank this one out in the calculator. And there's a lot of different reasons why you might do that. So, but anyway, I don't need to see y1 either. I just need to see y4. And actually, I don't even need to see that. But if I did want to see it, I can just say, graph, because the window, it may or may not be the same, but at least it'll be somewhere in the neighborhood of what it ought to be. Because in terms of the x values, it should be fine. But maybe you don't want to do that because it seems to be taking a while. But I can now go back, because y4 is talking about marginal profit. I can just run these calculations again and get those numbers just based off of my setup. So it's up to you. There's a lot of different ways to do it. You may look at this, and if I were in your position, I might be thinking the same thing, where it's like, why do any of that? It was very easy to take the derivative by hand. I'll just plug in the numbers. Yeah, but what if you have e to the cosecant of the natural log of the inverse sine of x as your function, right? So obviously not something that you would want to do by hand. I don't even know if that function makes sense. I just wanted to say something that sounded scary. That was the whole point. And the point was well taken, I think. something not as easy as just a polynomial function. All right. So then the explanation for something like this would be very similar to what we said for revenue. And in fact, it's almost the same, except replace revenue with profit and increase the numbers from part C with the numbers from part G. Profit is increasing at $4.10 for each additional saw, or each new saw if you want. And then profit would be decreasing at $15.70 for each new saw. Now, you're not expected to be experts in the field of table saws. So having a sense of what these numbers really truly mean in context, it's not, there are some expectations, but then there's some that would be unrealistic. So knowing that in this context, a positive number would be good and a negative number would be not so good, that's expected. Also knowing that certain types of positive numbers are better than other types of positive numbers. Same thing goes with the negatives. Like, just because you have profit decreasing doesn't necessarily mean that you're operating at a loss, because again, it's a rate of change. Just think of it this way. My profit could be decreasing at $15.70 for each new saw, but what if my profit is $140 billion? It's like, okay, yeah, it's going down by $15.70 for each new saw, but I'm not going into the poorhouse anytime soon, you know.
Table saw market.
Yeah, the table saw market is strong, you know. So, but what it does tell me is that I don't need to produce as many table saws. I can dial back my production, but what we can get from this is an optimal production. If I can figure out the moment where we have that transition between the positive and the negative, then I'd be in pretty good shape. All right. So that would be the idea there. All right. That would tell me my maximum profit under any circumstance. All right. But they ask us about something called the point of diminishing returns. That's something new. Conceptually, in terms of the calculus of it, it's not new. But in terms of as an application, it would be new. This is where we find the second derivative of profit. And we could do that by hand. That's easy enough because the constants are going away. It's just negative 0.0066. All right, a point of diminishing returns is an indicator, right? It tells us, it's kind of like an early warning system. It tells us when we need to start thinking about dialing back our production, right? So we're producing table saws, we're mass producing them, but at some point we're going to saturate the market and we're going to want to dial back the amount of table saws that we produce. Otherwise, we're going to be working against ourselves. So this concept will tell us when we're approaching our maximum, all right? So the second derivative gives us what's known as an inflection point. And let me just diagram that out for you. So let's say you have something that has a minimum point and it transitions to a maximum point, or a maximum point transitioning to a minimum point. The inflection point would be the transition. That moment in time inflection point. That moment in time when you're transferring from one type of extreme to another. So minimum to maximum, maximum to minimum. It addresses something called concavity, right? Because when you're talking about a part of a curve that is upward facing and therefore having a minimum, they call that concave up. You can see on this little interval, it's shaped like a U for up. Right? So that's been a mnemonic device for people in the past. The other orientation would be concave down. There's no, not to my knowledge anyway, fun mnemonic device for that, other than to say, well, if this one's the up, then that one can't be, so that must be the down. But also, it's facing downward, so, I mean, it should be easy enough. All right, but anyway, the inflection point is the transition between the two types of concavity, upward facing and downward facing, or downward facing and upward facing. But if you look at just this first situation, you can see that it's kind of like a precursor or a harbinger for the maximum point. All right, so it's kind of like that, what I was saying before, it's the early warning that a maximum point is on the way. All right, so if you can ever identify the inflection point, like in terms of a business, yeah, I mean, you're not there yet, obviously, you're not running your own businesses necessarily, but most of the time you can't tell that a maximum point is going to happen until it's already happened, right? You collect your data over time, sales over a period of time, and then it's like, oh, the maximum happened last month. I should have stopped producing 3 weeks ago. Wish I knew that a month ago. That sucks. All right, if only there was a way I could have got some kind of early indicator that that would have been coming up. The inflection point does do that. It tells us that we're getting closer to our maximum point. All right, so in any kind of function, if it's a continuous differentiable function on an interval, you could find the inflection point and it'll tell us whether or not a maximum point is on the way. All right, what does that tell us to do? It tells us that, okay, we're going to start thinking about slowing down our production because we're about to get to the moment where we will have optimized our profit. We would have gotten to the moment of maximum profit. We don't want to miss it. So now I know to keep my eyes open. So this is the alarm going off in the morning. At this moment, you hit snooze. This is when you wake up, all right? That's what an inflection point tells us, all right? In context, it's a great piece of information because, again, it's that early warning system. Now, what does it tell us when we get something that's constant? If you have a negative sign, it means that you're looking at an interval that's always, a negative constant specifically. It's always concave down. All right, so it's telling us that the entire graph would be downward facing. And that makes sense in this case because the profit graph was a parabola that was downward facing. And that's telling us that we should always be on the lookout for a maximum point. But if I had a variable in here, so forget about quadratic, maybe my profit function was cubic. When I take the derivative, I get something that, oh, actually, sorry, profit was linear. That's why I went constant. If the profit function was quadratic or cubic or anything higher, then I would have gotten something with an x in it. Then I would have gotten a particular number of table saws that would have told me, all right, now you need to start looking for that perfect moment in time when you would maximize your profits. Here it's telling us we always need to be on the lookout. So it's not as conclusive. We don't have a point of diminishing returns, a specific point, but we do have useful information, all right? But the idea is to look for the second derivative. If there's a variable, you're going to set it equal to 0 and solve for whatever the variable is. All right. So just make a note here. Take the second derivative. Set equal to 0 and solve. All right. A point of diminishing returns only happens in the transition from concave up to concave down. All right. Now, if you needed to find the maximum profit would be when the slope of your curve goes to 0. That would just be taking my derivative of profit and setting it equal to 0 and solving. All right, but that's not what they asked, so here we are. All right.